This video is all about giving you intuition into resistors, capacitors, inductors, and diodes, the nasty way. Okay, resistance shrinks in parallel. And the way I imagine that is with everyone's favorite analogy, the school bus fire. So we're driving along on the interstate. It's busy, busy, busy. And we have a huge school bus fire, and therefore there is a traffic jam. And the traffic velocity reduces to a halt. We are being resisted by this traffic jam. Resisted, come on. Resisted by the traffic jam. Well, what? And the big thing is there's 0 exits over here. No exits. We have to go through the resistance of the traffic jam. All right. We have the same exact school bus fire, same exact situation, except we changed one thing. And that one thing is we've added 3 exits. So now we'd still have resistance. It's going to be slowed down if we have to travel past the fire. There's always, cops and stuff in the way. So we still have resistance here, which I will draw like this. But because we have other options, we've thinned out the number of cars that have to go through, we can all travel a little bit faster. Actually, quite a bit faster than in this situation where we're all, I almost forgot, transform. Yeah. Than in this situation. So we can travel a lot faster here than we can here. And we could draw this situation electrically. So we'll say plus 5 volts. Why not? And we have 1 resistor and ground. And that's this one on the left. And then on the right, plus 5 volts. And we have resistor number 1, number 2, number 3, and number 4. Yeah, those kind of got nasty. What else? What else is new? You like it nasty. You like it. All right, and we'll ground these. And so by putting the resistance in parallel, we've kind of spread out the load in a sense, and we've given our little electron friends more choices. And in the event there is some kind of physicsy traffic jam, well, they can easily just decide to go around. And ultimately, this reduces resistance. That's the way I remember it. Okay, so now we're talking about resistors in series. And once again, our resistor is a school bus fire on the interstate. So we're traveling along, we're going up. Once again, we encountered the first school bus fire. We have nowhere else to go. We just got to deal with it. Let's just say we have to wait an hour. Well, 1 mile up the road is another school bus fire. Once again, we wait 1 hour. And then 1 mile up the road is another. You get the idea. 1 hour, 1 hour, 1 hour, that's 3 hours. Resistors add up linearly. And that's exactly what the schematic would look like. Well, this is an ugly-ass schematic, but let's go ahead and put the correct pluses and conventional current, boys and girls. 1 resistor, 2 resistors, 3 resistors. They add up linearly. A voltage divider is a big, strong man here holding up a big damn truck here. Gravity is pushing down. He's pushing back up. Okay, and so let's get into this. First off, this is the symbol for a resistor from Britain. I apologize deeply. I do not like to ever use anything from Britain. But therefore, I've redrawn it American style, much nicer, by the way. These are the same thing. They're interchangeable. So they're both 10K resistors in our case. And so the idea here is we give it 5 volts. The signal goes through a resistor. We have our little node where we're going to take the voltage. That's what we really care about in this particular case. And then we have another 10K resistor that goes to ground. So the way I like to think about this is we really put a lot of thought. Hey, I said pencil. We put a lot of thought into this bottom resistor. So what if this bottom resistor was small? What if it was so small it went to 0? And so a resistor that goes to 0 ohms is just a wire in our little ideal case here. Ignoring all the fancy nasty stuff that goes in there. And so if we want to take that same voltage, what is the voltage right here? Well, we have a ground to 0 and it's connected. So this is V equals 0. Where'd my pencil go? Why am I using a mouse? So therefore, this is 0 volts. And so if we had a really small resistor, what if we put a 10 ohm resistor in right here? I'm not going to do the math on it right now because I can't do that in my head. But 10 ohm resistor, that would just barely be holding this thing up. Whereas like a mega ohm resistor would be really holding this thing up. And so when I imagine the big strong man holding up the truck, what happens if he doesn't put any force in the upper direction? Well, we have gravity pushing down and splat city. So the bigger, the stronger the resistor, the bigger the voltage right here. So the voltage divider is all about this bottom resistor really, and it's a ratio of the two really, but the most important part is by far the value of the bottom one. And that's why the equation for voltage divider uses the bottom resistor on top. Let's talk about capacitors. Today we are going to kill my brother with a capacitor analogy. All right, let's hop to it. All right, so we know that we've probably seen the pool metaphor, but I'll kind of show it to you anyway. I have a better spin on it. First, we have water traveling along a hose. The water shoots out of the hose into a swimming pool. The swimming pool stores water, and until it gets higher and higher and higher, until it gets to this point right here. Once the water is right here, it will start overflowing into my little pan here, my smaller pool. That water will collect. When enough water collects, it will smash down on my brother and kill him. Well, that was supposed to be blood. Let's try this again. He's dead. Take that, jerk. Okay, so how is this equivalent to electrical stuff? Well, for one, instead of water, we have current flowing through the hose. The pool is our capacitor. When the pool is full of enough current, it really stores charge, but current is just a flow of charge, so it's whatever. So once enough charge is all stored up in here, and once the charge is full, the capacitor is full, then we suddenly develop a voltage. Now, it just so happens a voltage is a force, and the force will be used to destroy my brother. That's what we're trying to do here, I guess. And so you can see the electrical equivalent over here. You can see where I was practicing. We have 5 volts. We give it some juice. Oh, no, we have an empty capacitor. Well, forget everything over here. The capacitor is the top dog. You ever seen dogs, like the dominant dog, if you feed like multiple dogs at once? He'll bark at everybody and growl and snarl. He'll eat all the food, and then the wimpy dogs get to eat afterwards. And that's the capacitor is the top dog here. The capacitor is more or less a short to ground. It pulls a ton of current, and it'll take everything you get it until it's charged. Once it's charged, its belly is full, and it's like he's not even there. Current just flows that way, and we have our precious little voltage we wanted. This is the least clever, most idiotic metaphor of the whole video. Let's talk about capacitance. What happens when we have a bunch of capacitors? Like these 4 are in parallel. Do they get smaller? Does capacitance go down? Or does capacitance go up? Well, capacitance goes up. And the way I'm trying to force this is I have raging fat ass disease. I don't know if you've noticed it. But let's just say after a workout or just for any other reason, I'm ready to eat a ton. Well, what's better? 4 plates of food or 1? Well, 4 is better. Man, this metaphor makes no sense. I don't know if there is a good one. At least I wrote satanic fork over here. Here's the deal. When you're looking at these 4 capacitors, these all do add up. They're in parallel. And the way you think of that, I guess, is more of a literal, like actually what's going on. Where am I spit? There it is. So, uh-oh. What was that noise? So a capacitor. So a capacitor is 2 parallel plates put together. Now, the bigger this plate right here, the more capacitance this plate. Well, one way to make that plate seem bigger is just to use 2. And assuming these were equal size, we have now doubled it. So we have this much area and this much area from here to here, here to here. Kind of nasty, isn't it? Now it's really nasty. So I guess I don't know what any other way to remember this then, but I know this has saved my ass in school many times, and a lot of people struggled with this idea of capacitance. And just remember that the capacitors are a plate, and the bigger the plate, the bigger the capacitance. I mean, it's as simple as that. And the equation, once again, I'll post it up on the screen. It looks a little nasty, but the area is on top, and that area would be the area of the plate. Hang on. Man, is that helping? Not really. Again, work with me here. Some of these are harder to be nasty on than others. Again, at least I wrote satanic fork over there. Okay, let's talk about capacitors again. Capacitors block DC. Just remember that. Capacitors block DC. And so, right here, it's our dad. He's the capacitor. And here is DC. DC Young Fly. I had to Google him. I never heard of him. I haven't listened to much rap since Snoop Dogg. And maybe some Eminem. Anyway, so DC Young Fly wants to date the daughter. Angry dad says, no way, DC. I block DC. I am a capacitor. Oh, I think my timing is now off. I am a capacitor. Okay. Scroll down, though. But now we have AC. AC Green. I didn't have to Google him. He was on the Lakers, as you could see, back in the old days, Magic Johnson times, my era of basketball. AC Green says, hey, Dad, can I see the daughter? And Dad says, sure. Oh, wait, he's not supposed to be angry. He's just Dad now. Come on in. Come visit. He likes AC Green. He doesn't have neck tattoos. Okay, so as far as this blocking DC business, we've talked about the swimming pool thing, where if we charge up this capacitor and this one and all these capacitors are charged, then we develop a voltage. Well, once this capacitor is charged, another way of looking at it is this capacitor is blocking 5 volts from getting to ground. If it's not charged, it flows right on through. But once it gets charged, it's blocking. And that's kind of what the symbol is kind of indicating in some levels. And so DC will not get through. Now, in this particular situation, once these capacitors are all charged, DC will go this way. And we'll have a DC voltage. We'll call this VDC right here. Now, AC voltage, on the other hand, which we can easily do, we can make a signal. Let's say it's 5 volts up here. But then we have an AC component too. So we have like a sine wave that happens to be like this. Let's just say it's 1 kilohertz. 1 kilohertz will go the AC part of that, the changing part will go down, but the DC component will stay the same. And so this is the input that I just made up. So then your output will just be 5 volts. And so that's part of the significance of blocking DC but allowing AC. This comes up a lot when designing amplifiers and things of that sort. But just remember, capacitors block DC. Okay, so let's talk about the equation for capacitive reactance, which is essentially the resistance of a capacitor at a given frequency. You can look at capacitors as, there's our capacitor, as one of these, just a resistor, but it's only at a certain frequency, and it's going to change dependent on frequency. That's kind of the whole point of the capacitor thing. So XC is reactance. It's the same thing as resistance, sort of. It's just a way of saying there's going to have frequency in there. Okay, so we have the capacitive reactance is 1 over J boobies C, which boobies is actually omega in Greek, which is actually 2 pi F, F being frequency. So let's rewrite this as capacitive reactance equals 1 over 2 pi FC, C being for capacitance. So if frequency of a DC signal, FDC, equals 0 hertz. If we toss 0 in for F, we have infinity. So the capacitive reactance at 0 hertz is infinity for a capacitor. That's how we that's how we combine the math with the. I just wanted to make sure we kind of combined the concepts with some of the math you'll see in school. Again, that's kind of the whole point of these videos. Is school has one way of teaching, and then there's actual intuition, but mixing those together is kind of difficult. So hopefully this helped a little bit. And this one is the nastiest of them all. We're going to talk about the relationship between capacitors and inductors. And it's nasty not because I got blood and guts and fart and shit on it. It's because it's kids. It's young 8-year-old kids. I don't know if you've ever been around these damn things. They're terrible. And that's another story. But in particular, we have Alex, who's my niece. Where are you at, marker? Transform. We have Alex, my niece. She's 8 years old. She's a girl. Have my son, Max. He's 8 years old. He's a boy. And they're close. Very close. And therefore, they're kind of like brothers and sisters. Therefore, they hate each other. And so Alex will say, we'll be like, hey, Alex, what do you want for supper tonight? And she goes, I love tacos. And then for no reason at all, even though Max actually agrees with her, he'll go, I hate tacos. He is going to do the exact opposite of whatever Alex does just for spite. And this same relationship occurs for inductors and capacitors. So you could think of inductors and capacitors as cousins that are very close, or maybe even brothers and sisters. And the reason I say they're the opposites is the equations for parallel capacitors in parallel add up. We just talked about that. Inductors in parallel shrink. And same thing in series. Inductors in series, get bigger. Capacitors in series shrink. And it just so happens, just a little tidbit, inductors always follow this. Oh, golly, I was in my zone. I was killing it this time. Inductors use the same equations for adding and in series or parallel as resistors do. So remember, they're on the same team. So I don't know if that helps you or not, but thinking of inductors and capacitors as opposites, it holds up a whole lot, especially early on. Enjoy. Okay, so let's show some examples of capacitors and inductors fighting like evil cousins. Okay, impedance. Whew. Hey, do what I want to do. Impedance. Impedance, again, is just resistance at a certain frequency. It's the exact same thing as resistance, but we have to remember to account for frequency. That's the difference. So we have this capacitor, mostly a capacitor. The impedance of a capacitor is 1 over J booby C, although that looks more like cat claws today, so 1 over J cat claw C, and cat claws is 2 pi F, 2 pi times frequency. So with the frequency on the bottom, when the frequency goes to 0, resistance goes to a zillion. When frequency goes to infinity, this thing goes to 0. So we're blocking DC, we're leaving AC alone. Well, an inductor is the exact opposite. It blocks AC, and more so the higher the frequencies you go, as you can see here. We've got J cat claws L. So it's frequency right here. Frequency goes up. Impedance on the inductor goes up. So it's the exact opposite. They completely argue. Let's give another example. The way we think about capacitance is it's a change in voltage over a change in time times the capacitance, and that'll give us a current. Whereas inductance, on the other hand, will give us a voltage across that inductor, but it's the change in current. And essentially, they just both pick the opposite path every time. Inductors pick current, capacitors pick voltage. So these are two examples. There's many more, phase angles, lead and lag, and all kinds of fancy stuff that doesn't really come up as much in my world so much. But for intuition's sake, just remember that inductors and capacitors fight like brothers and sisters or evil cousins. Okay, let's talk about diodes. I need to read this. A diode is a never convicted straight man's butthole. Exit only. Okay, you heard it first. I'm going to hell for that one, I'm sure. Okay, let's figure this out. So here's the symbol for a diode. The symbol is slightly tricky, and then in the roll of this line seems weird. It seems like you go through the arrow. The arrow is clearly telling you go to the right, but then you hit this brick wall. The brick wall only applies whenever you run into it first. All right, that's the big takeaway. After that, the diode symbol makes total sense. The thing you hit first is what you follow. So, you see an arrow, current goes that way. That's allowed. You go this way. Vroom. Another way to look at a diode is a one-way street. That's boring. Again, you only allow things one way. Now, it's probably, let's go back to the what is it? Again, let's go back to the never convicted straight man's butthole analogy. This is a toilet. This is a man. I am not going, he's supposed to be sitting down. I'm not going to get into details, but let's just say the one-way street method, taking a crap, isn't free either. It's not fun. It's called forward voltage loss. I don't know how crapping has anything to do with the forward voltage loss, but whenever you cross this line, you pay a penalty right here. And that penalty is, generally speaking, or considered, at least in school, 0.6 volts. In real life, it varies from diode to diode. So that means if you have 5 volts and then a diode, and there, that's a 5, trust me, then you got 4.4 volts for all practical purposes here. Some people assume it's a little more or a little less. You kind of have to be careful, but I like the 0.6 number. In real life, it gets a little bit lower than that sometimes, especially with small SMD components. So, I don't know if the exit-only butthole strategy is your style. Have fun with that. I warned you I was going to be disgusting. I'm having fun. You know, you can just hit dislike if you want. I understand. Okay, boys and girls, so that's it for today. I will be posting videos every week. I don't expect to be doing too many about school and intuition anymore. I don't expect to have to use my little drawing pad. Yeah, like you can see this drawing pad. It's a XP pen, by the way, not a bad product. I will be doing a lot more electronics things. I have all kinds of projects I'm building. A lot of this channel is going to be me screwing things up. I don't think I'm not very competent. I've kind of covered that in my little intro picture. I will screw things up more. It's going to be watch me fuck up, I think, is probably where we're going with all this. But I think you will learn stuff, and we will have, hopefully, more boobies, cat claws, and buttholes. So if you don't like this, don't subscribe. And if you do like this, don't subscribe. Don't follow me on Patreon. Don't hit like.